Right now, a star 700 times wider than our sun is dying. Betelgeuse burns through the equivalent of our entire sun every 6 million years. But here's what most people don't realize. When this red giant finally explodes, it could happen tomorrow or in 100,000 years. And we'll have just 8 minutes warning. Today, we're traveling to the cosmic time bombs lurking in our galaxy. Stars that rain liquid metal, binary systems locked in death spirals, and gamma-ray bursts that could sterilize half our planet. If you're ready to explore the universe's most dangerous neighborhoods, hit that like button and subscribe. Prepare yourselves. We begin. Music. In the shoulder of Orion, a star larger than Jupiter's orbit around our sun is running out of time. Betelgeuse has been burning for 10 million years, but now it faces a problem that will kill it. Deep in its core, the nuclear furnace that kept this giant alive is starting to flicker. Think of it like a massive campfire that's been burning for millions of centuries, and now the logs are almost gone. What makes Betelgeuse so dangerous isn't just its size, though that's mind-bending enough. If you placed this red supergiant where our sun sits, it would swallow Mercury, Venus, Earth, and Mars completely. The surface of this monster would stretch past the asteroid belt. Picture our entire inner solar system as just a tiny bubble inside this dying star. The real threat comes from what happens when stars this massive run out of fuel. Unlike smaller stars that fade gently into white dwarfs, Betelgeuse has grown too large to die quietly. When the nuclear reactions in its core finally stop, gravity will crush the star's center in less than a second. The collapse happens so fast that the core becomes smaller than Manhattan while weighing more than our entire sun. Then comes the rebound. All that crushed material bounces back and crashes into the star's outer layers at 30,000 meters per second. The collision creates an explosion so powerful it outshines entire galaxies for months. We call this a supernova. And when Betelgeuse goes supernova, it will be visible during the day. Here's what keeps astronomers awake at night. This red giant has already started showing signs of instability. In 2019, Betelgeuse dimmed dramatically, making scientists wonder if the explosion had begun. The star recovered, but these changes tell us the end is approaching. The question isn't if Betelgeuse will explode. The question is when. The uncertainty comes from stellar timescales. When astronomers say a star will explode soon, they mean sometime in the next 100,000 years, which is basically tomorrow in cosmic terms. Betelgeuse could detonate while you're reading this, or it might wait until your great-great-grandchildren are gone. We simply cannot predict it more precisely. What we can predict is the aftermath. When Betelgeuse explodes, the light will reach Earth in about 600 years. For several months, our night sky will have two bright objects that look like suns. Ancient cave paintings might have recorded similar events from other stellar explosions, showing how these cosmic fireworks impressed our ancestors. The explosion will be spectacular, but Betelgeuse sits far enough away that the deadly radiation won't sterilize our planet. We'll get front row seats to one of the universe's most violent events while staying perfectly safe. This makes Betelgeuse unique among dangerous stars. Most cosmic threats would kill us before we could appreciate their beauty. This red giant offers us something different, a countdown to the greatest fireworks show in human history. However, what makes a star truly dangerous goes far beyond simple size. The deadliest stars in our galaxy all share one terrifying feature. They're massive enough to forge iron in their cores. Most people think bigger automatically means more dangerous, but stellar physics works differently. A star becomes a cosmic weapon when it grows beyond 8 times the mass of our sun. This threshold determines everything about how a star will die and whether it poses a threat to nearby worlds. Think of stellar mass like a pressure cooker. Small stars like our sun can only squeeze hydrogen and helium together, creating gentle fusion reactions that last billions of years. These lightweight stars die peacefully, puffing off their outer layers to become beautiful planetary nebulae. They're the cosmic equivalent of a candle burning out. Massive stars operate more like nuclear reactors on the edge of meltdown. The immense gravitational pressure in their cores forces increasingly violent fusion reactions. First, hydrogen burns to helium. Then, helium fuses into carbon and oxygen. The temperatures climb to hundreds of millions of degrees as heavier elements form. Neon, magnesium, silicon. Each new element requires more energy to fuse than the last. The star burns through its fuel faster and faster, like a car racing downhill with failing brakes. A star with 20 times our sun's mass might burn hydrogen for 10 million years, helium for 1 million years, but silicon for just 1 day. The real danger begins when the core starts producing iron. Iron nuclei refuse to fuse into heavier elements because the process would absorb energy instead of releasing it. When iron builds up in a massive star's center, it's like filling the nuclear furnace with wet logs. The fire goes out instantly. Without fusion energy pushing outward, gravity crushes the core in less than a second. The collapse is so violent that protons and electrons get mashed together into neutrons, releasing more energy than our sun will produce in its entire 10 billion year lifetime. This energy tears through the star's outer layers and launches them into space at 10% the speed of light. The explosion creates temperatures of 100 billion deg, 6,000 times hotter than the sun's core. At these extreme conditions, the dying star forges elements that cannot form anywhere else in the universe. Gold, platinum, uranium. Every heavy atom in your body was created in the final seconds of a massive star's life. Distance determines whether the stellar death becomes spectacular or catastrophic. A supernova 25 light-years away would strip away Earth's ozone layer and trigger mass extinctions. The same explosion 100 light-years away provides a beautiful light show with minimal damage. The most dangerous stars combine massive size with close proximity to Earth. Astronomers have identified dozens of supernova candidates within threatening range of our solar system. These cosmic time bombs could explode tomorrow or in millions of years, and we have no way to predict exactly when. What makes this even more unsettling is the sheer scale we're dealing with. Understanding just how large these stellar monsters grow requires stepping outside everything we know about size. If our sun were the size of a basketball, the most dangerous stars in our galaxy would be larger than football stadiums. Scale becomes meaningless when dealing with the universe's largest stars. We need to build up to their true size step by step using comparisons that make sense to human minds. Start with something familiar: Earth. Our planet measures about 8,000 meters across, which seems enormous until you realize that 1 million Earths could fit inside our sun. Our sun spans 864,000 meters from edge to edge. Light takes 4.5 seconds to travel across its diameter. This makes our sun a fairly average star, sitting comfortably in the middle range of stellar sizes. Picture it as a bright yellow marble in the cosmic collection. Now imagine a star 50 times wider than that marble. This brings us to red supergiants like Betelgeuse, where the word large stops making sense. If Betelgeuse replaced our sun, Earth would orbit inside the star itself along with Mars and everything closer than the asteroid belt. The International Space Station would be flying through stellar atmosphere instead of empty space. Red hypergates push size into the realm of the impossible. Stars like Vicinus Majoris measure more than 1 billion miles across, so large that light takes 6 hours to travel from one side to the other. An airplane flying at 500 meters an hour would need 2,000 years to circle this monster once. Here's a comparison that might help you grasp the scale. If Earth were a grain of sand, our sun would be a large. Vicinus Majoris would be a sphere taller than the Empire State Building. The volume difference is so extreme that you could fit 7 billion of our suns inside this hypergiant. These massive stars burn so brilliantly that they're visible from millions of miles away. Vicinus Majoris shines with the power of 300,000 suns combined. If you replaced our sun with this hypergiant, the surface temperature on Earth would instantly rise to 3,000 degrees F, hot enough to melt copper. The physics of such enormous stars barely make sense. Their outer atmospheres are so loosely held that stellar winds constantly blow material into space. These dying giants lose mass equivalent to our entire Earth every few million years. Yet, they're so massive that this loss barely affects them. What's truly mind-bending is that these stellar behemoths live fast and die young. While our sun has enough fuel to burn for 10 billion years total, a hypergiant exhausts itself in just 3 to 5 million years. That's less than 1,000th the lifespan of an average star. The largest stars we discovered are so unstable that they pulsed and vary in brightness over periods of months or years. Their outer layers expand and contract like the slow breathing of a sleeping giant. Each breath cycle moves stellar material across distances larger than the orbit of Jupiter. When these cosmic monsters finally die, they don't just explode. They detonate with the fury of 10 billion hydrogen bombs every second. The death of a massive star unfolds in 3 devastating phases, each more violent than anything humans have ever witnessed. Phase 1 happens in the final seconds, before collapse. Deep inside the dying star's core, iron nuclei pile up like nuclear ash in a cosmic fireplace. For millions of years, fusion reactions have supported the star against its own crushing gravity. But iron changes everything. Instead of releasing energy when it fuses, iron absorbs energy, effectively killing the nuclear fire that kept the star alive. Without energy pushing outward, gravity wins instantly. The core collapses from the size of Earth to 12 meters across in less than 1 second. Imagine crushing a basketball down to the size of a marble in the blink of an eye, while somehow keeping all the original mass. The density becomes so extreme that a teaspoon of core material would weigh as much as Mount Everest. During this collapse, something remarkable happens. Protons and electrons get squeezed together so hard they merge into neutrons, releasing floods of ghostly particles called neutrinos. These neutrinos carry away 99% of the explosion's energy, racing through the collapsing star and out into space at nearly the speed of light. Phase 2 begins when the collapsing core hits the point where even neutrons cannot be compressed further. This creates a shock wave that bounces back toward the surface at 18,000 meters per second. Think of it like dropping a rubber ball on concrete. The core rebounds with incredible violence, sending a wall of energy racing through the star's outer layers. The shock wave takes several hours to fight its way to the surface, pushing through layers of silicon, oxygen, neon, and hydrogen. As it travels, the wave heats material to temperatures exceeding 5 billion dig. This is hot enough to forge elements heavier than iron, gold, platinum, and uranium. All form in these final moments of stellar death. Phase 3 is the spectacular finale we call a supernova. When the shock wave breaks through the star's surface, it launches the outer layers into space at speeds of 6,000 meters per second. The explosion releases more energy in 10 seconds than our sun will produce in its entire 10 billion year lifetime. The light from this cosmic detonation can outshine an entire galaxy containing 100 billion stars. If a supernova happened 25 light-years from Earth, it would appear as bright as the sun in our daytime sky. The explosion would be visible to the naked eye for months, slowly fading as the expanding debris cloud cools and disperses. The aftermath creates one of 2 exotic objects. Stars between 8 and 25 solar masses leave behind neutron stars. City-sized spheres so dense that gravity at their surface is 200 billion times stronger than Earth's. More massive stars collapse completely into black holes, creating regions where gravity becomes so strong that even light cannot escape. The expanding shock wave doesn't just create heavy elements. It launches them into space at incredible speeds, seeding the galaxy with materials essential for planet formation. A supernova shock wave travels through space like an invisible tsunami, carrying enough energy to reshape entire regions of the galaxy. When the explosion first erupts from the dying star's surface, it moves at roughly 6,000 meters per second, fast enough to circle Earth in 45 seconds. This expanding sphere of superhot gas and magnetic fields doesn't slow down quickly. Even after traveling for thousands of years, supernova remnants maintain speeds of several hundred miles per second. The shock wave pushes against the thin gas that fills space between stars, creating a bubble of destruction that grows larger every year. Think of it like a bomb exploding underwater. The blast creates an expanding sphere that pushes water aside as it grows. In space, the supernova remnant pushes aside cosmic gas and dust, heating it to millions of degrees and accelerating particles to incredible energies. These cosmic shock waves can travel for hundreds of thousands of years before finally running out of steam. The Cygnus Loop, a supernova remnant visible through telescopes, spans 70 light-years across and is still expanding from an explosion that happened 20,000 years ago. That's a bubble large enough to contain 2,000 solar systems like ours. The destructive power of these blast waves depends entirely on distance. Within 30 light-years of a supernova, the shock wave would strip away planetary atmospheres and sterilize any worlds in its path. The radiation levels would be thousands of times higher than anything life on Earth could survive. At 50 light-years away, the effects become more subtle, but still dangerous. The blast would damage our ozone layer, allowing deadly ultraviolet light from the sun to reach Earth's surface. This could trigger mass extinctions by disrupting food chains that depend on plankton and plant life. Some scientists think supernova explosions might have caused several of the major extinction events in Earth's geological history. Beyond 100 light-years, supernova shock waves become less threatening to life, but more important for astronomy.